Greetings, class. This is Lesson 4, Finite Sample Spaces. Let's start out with the sample space S that's finite, meaning that there are only a finite number of possible outcomes of the experiment. Since there are only a finite number, let's list them out. Little s1, little s2, ... little sn. It turns out that finite sample spaces usually allow us to calculate the probabilities of certain events way more efficiently. To illustrate, let's suppose that A is some arbitrary event in the sample space. Then the probability of A equals the sum of the probabilities of every element that happens to be in A, every outcome that happens to be in A. We'll illustrate more precisely with an example. Suppose that we have two red cards, a blue card, and a yellow card. What we're going to do is we'll pick one of them at random, where we all kind of know what at random means, simply that each of the four cards has the same probability, 1/4 being chosen. The sample space for this experiment is just seeing the outcomes red, blue, and yellow. And those can be denoted little s1, little s2, little s3. So for instance, if we see red, that corresponds to the outcome little s1. So because there are two red cards out of the four, you can easily see that the probability of a red card, the probability of the outcome little s1, is a half. The probability of s2, which is a blue card, is a quarter, and the probability of a yellow card, s3, is also a quarter. So let's look at the event red or yellow. That's A, my event A. Since red or yellow, those two outcomes are disjoint from each other, I can break up the red or yellow into the probability of S1, red, plus the probability of S3, yellow. 1/2 plus 1/4 equals 3/4. Pretty easy. Now let's make an even nicer definition. A simple sample space, SSS, is a finite sample space in which all outcomes are equally likely. Equally likely is important. So in that last example, S was not a simple sample space because the probability of the different colors, those probabilities were different. We had a half, we had a quarter. As an easy example, let's toss two fair coins. So the sample space that I'll look at is the sequence of potential observations: heads, 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 tails, tails, heads, and tails, tails. This is a simple sample space because all those probabilities of the four outcomes, the four sequential outcomes, are all 1/4. Let's look at another sample space, S prime, which denotes the number of heads, and that, of course, can only be 0, 1, or 2. That is not a simple sample space. Why not? Well, the probability of having two heads, so the number 2, that's 1/4. Heads, heads is probably a quarter. The probability of having 0 heads, tails, tails, is also a quarter, and the probability of having exactly one head is a half, because you could see heads, tails, or tails, heads. So that's not a simple sample space. Here's the main theorem why I like simple sample spaces so much. For any event A in a simple sample space S, wow, you don't see 4 S's in a row very often, but there you go. For any event A, the probability of A is merely the number of elements in A, the cardinality of A, divided by the number of elements in S. Really easy, and we'll illustrate now. Let's toss a die, and we'll let the event A be the outcomes 1, 2, 4, and 6, each of which has probability 1/6. So that means that the probability of A is the cardinality of A over the cardinality of S, 4/6. Very, very easy. Here's a nicer example. Let's toss a pair of dice. Possible results, each with probability 1/36, are 1, 1, 1, 2, ... 1, 6, all the way down to 6, 6. So these guys are ordered pairs where the first number is the result of the first die, the second one is the result of the second die. So each one of those equal probabilities, there's 36 of them, and so each one has probability 1/36. And if we want, it's possible to calculate the probability of any possible sum. So the sum being 2, that's an event. The event that we observe a sum equal to 2. The event that we observe a sum equal to 3, 4, all the way up to 12. The only possible sums are 2, 3, 4, up to 12. And below those sums, I have the calculated probabilities. 136, 236, all the way up to 636, which peaks at a sum of 7, and then goes back down to 136 when we get to a sum of 12. Let me illustrate how we got these numbers. For example, what's the probability of the event A being that the sum is equal to 4? Well, the only way that I can have sum equal to 4 is if I observe the ordered pairs 1, 3, 2, 2, and 3, 1. There are 3 ways to do that, 136 plus 136 plus 136, and I get my answer then of 336. And you can see if you go a little table, the probability that the sum is equal to 4 is 3 over 36. And you can similarly calculate all those other probabilities. By the way, if you ever want to go to the gambling table, to get a sum equal to 2, there's only one way you can do it. Get a 1 and a 1. That is sometimes called snake eyes. And sum equal to 12 you can achieve by getting a 6 and a 6. That's called boxcars. With this material in mind, we can move on to more complicated counting problems, and those are going to be the subject of the upcoming 3 lessons. So we'll see you in a little while.